This is going to be a discussion about derivatives and rates of change. So to start this discussion, we're going to go back to the tangent line problem. It's something we introduced already before we had had a conversation about the concept of a limit. So now that we've laid some really good groundwork about limits and continuity, we're going to just do a quick revisit to the tangent line problem. So remember that that problem involved finding the equation of a line tangent to a curve at a specific point. So the specific point we named A and f of a. If the x-coordinate is a, then its y-coordinate will be f of a. And we're looking to find the equation of the tangent line. Well, remember, if you're looking for the equation of a line, really you need two pieces of information. A point on the line, and you need the slope of the line. Well, we have a point on the line. That's this a, f of a. So really what the challenge becomes is finding the slope of the tangent line. So if you have a generalized curve, call this f, and a point on that curve, let's put it over here, and that'll be my point P, and it has coordinates a, f of a. So it's got an a on an x value and f of a as its y value. In order to find the slope of the tangent line, so that will be the slope of this line right here, that's your tangent line. The problem is we only have one point on that line. So the way we started the tangent problem was we said, okay, well, if we need a second point to be able to calculate slope, let's just pick a second point, call it Q, and give it coordinates x, f of x, meaning it could represent any x value on the curve. So x, f of x. If you find the slope of the secant line, now that you have 2 points, finding the slope of the line, not really too problematic. It's just y value minus y value minus y value, so f of x minus f of a over x minus a. This was the slope of the secant line, which is an estimation of the slope of the tangent line, but not really a good one. So if you wanted the slope of the secant line to be closer to the slope of the tangent line, you needed to slide the point Q closer to the point P. And in doing so, you're letting x get very, very close to a. So that was the limit as x approached a on f of x minus f of a over x minus a. That is the slope of a tangent line. So now that we've discussed limits, we can precisely define what we mean by a tangent line. If you recall, the best definition that I had for you was that a tangent line would hit your curve once at the point, and it would follow the direction of the curve. And I mentioned at the time that's not a very good, precise definition. Well, now we've got a better one. The definition of a tangent line to the curve y equals f of x at the point P, which has coordinates a, f of a, is the line through P that has the slope that we just talked about. So if you leave off the limit sign, this is the slope of a secant line. But once you put that limit on there, it's not the slope of a secant line, it's now the slope of a tangent line. So the slope of the tangent line is the limit of the slopes of the secant lines as the change in x gets smaller. So as you move that second point closer and closer and closer to P, the more the slope of the secant lines approach the slope of the tangent line. So the example that we completed, we found the equation of the line tangent to the curve f of x equals x squared at the point 1, 1. Now, if you remember, we had to do this numerically. We set it up so that the slope of our secant line, m, was going to be the slope between the point 1, 1 and then the general point, which had an x-coordinate of x, and then because it was on this curve, its x-coordinate was x squared. So it was x squared minus 1, so the y value minus y value, over x value minus x value. That's this one over here. So we did it numerically, and we said, okay, we're going to let x get kind of close to 1. So we started with x equals 2. We did our calculation and got 3. When x was 1.5, we got 2.5. This should all look familiar. This is all the example we went through. So by the time we were done, we were looking at the slope of the secant line, and as x got closer and closer and closer to 1, the slope of the secant line was approaching 2. So we guessed that the slope of the tangent line was therefore 2. Now we can find the slope of this tangent line without guessing. Instead of the slope of the secant line, which was the f of x minus f of a over x minus a, we're now looking at the slope of the tangent line. Since the slope of the tangent line is the limit of the slopes of the secant lines, this is our slope of our tangent line. So our a, which is the x-coordinate of our fixed point P, our a is going to be equal to 1. And remember, our function for this problem is x squared. So we'll have the limit as x approaches 1 on f of x, which is x squared, minus f of a, which is your function with a plugged in. That was 1. Technically it's 1 squared, which is 1, over x minus a. Well, this is a limit we can calculate. We notice that x squared minus 1 is the difference of two squares. That's x plus 1 times x minus 1 over x minus 1. The x minus 1's cancel, and what we get is the limit as x approaches 1 on x plus 1. Well, that's a polynomial eligible for direct substitution, and there we have it. The slope of our tangent line is 2. It's not a guess. It's not an estimate. This limit is exactly equal to 2. Now for the tangent problem, there actually is a second set of notation that we use interchangeably. Instead of referring to the slope of the tangent line as the limit as x approaches a of f of x minus f of a over x minus a, sometimes we'll use notation that looks like this instead. The problem stays the same. We still have a curve and a point on the curve, call it P, that we are attempting to find the equation of the tangent line, which actually means we just need to find the slope of the tangent line. And its coordinates are a and f of a. It's what we call Q that we change up our notation just a little bit. Instead of calling Q x and f of x, what we do is we say that the x-coordinate of Q is just slightly beyond the x-coordinate of P. So instead of calling it x, we call it the x-coordinate of P, which is a, increased by some small value h. Remember, we want P to slide close to Q, so we want h to be very small. Well, if the x-coordinate of Q is a plus h, then its y-coordinate is f of a plus h. So we still want the slope of the tangent line based on this notation. It's going to change up how it looks just a little bit. It still contains the difference in the y values divided by the difference in the x values with a limit in front. But now your y values are f of a plus h and f of a. And then your x values are a plus h minus a. And yes, these two a's will cancel and just give you an h down in your denominator. And then the limit changes a bit as well. We're still sliding Q close to P, but instead of saying a plus h gets close to a, which it does, instead what we do is we consider this. What is the distance between these two x values at the moment? Well, if this one's at a plus h and this one's at a, the distance between them is h. So you want the distance between them to get very small. So in other words, you want h to approach 0. So you will often hear us refer to, well, should I be using the x goes to a notation or the h goes to 0 notation? We will use both. Believe it or not, we more often are going to use the h goes to 0, but we definitely use both. You can generalize this even more. Instead of referring to this as h, sometimes you'll hear it referred to as just a change in x even. So instead of calling it h, if you call it change in x or delta x. So it's the x-coordinate of q would then be the x-coordinate of p increased by some small change in x, in which case the h is now a delta x. And then this is what you get instead. Here's your y value, f of a plus delta x minus f of a, divided by, technically this starts out as a plus delta x minus a, and then of course the a's go again, and you're left with just delta x, and then you'd call this delta x and let delta x go to 0. This is a very general way to write this. So those are some of the different notations you can see for this concept. So let's take a look at this question. We're going to find the equation of the line tangent to y equals 3 over x at 3, 1. So for this one, we're going to practice the h goes to 0 notation. So we are going to look at the limit as h goes to 0 of f of a plus h. Now, since we are fixing our point that we're looking for the tangent line at 3, 1, what is a for this particular problem? A should be 3. So that's the limit as h approaches 0 on f of, that's going to be 3 plus h, minus f of a, so minus f of 3, all over h. This is the limit that we're going to look to calculate, that it will give us the slope of the tangent line, which in turn will give us the equation of the tangent line to the curve y equals 3 over x at 3, 1. So we have the limit as h approaches 0. F of 3 plus h says take your function f, and everywhere you see x, you're going to plug in 3 plus h. So we get 3 over 3 plus h minus f of 3. Now you can do this one of two ways. You can either do it the same way we just did the 3 plus h. You can say this is my function with 3 plugged in which case you plug in the 3 and you get 3 over 3, also known as 1. Or you can just use the fact that we gave you the y-coordinate. The 1 is sitting right here. That's how the y-coordinate was calculated. So you can just pick it up from here if you prefer. And then that's going to be all over h. So this is the limit that I now need to calculate using the limit laws that we discussed. If we try to do direct substitution, you're going to plug in 0 in place of h. You'll get 3 over 3, which is 1, minus 1. You're going to get 0 over 0, which means it's an indeterminate form. When you're doing this particular kind of problem, you're always going to get an indeterminate form if you try to plug in this 0. So we're going to have to algebraically manipulate this. Now, if you remember the technique, this one has a complex fraction. It's fraction within fraction. So the goal is to get one fraction in the numerator and one fraction in the denominator so that we can then multiply by the reciprocal of the denominator. So the denominator's fine. This is h over 1. We got one fraction down there. It's the numerator that's the problem. What we need to do is we need to go ahead and subtract these two fractions. Technically, this is 1 over 1. The common denominator will be 3 plus h. This one already has it. So we consider 1 to be 3 plus h over 3 plus h. That will give us the common denominator that we're going to need in order to be able to subtract these. So when we put our numerator together, we get 3. Well, first we have the limit. So we have the limit as h approaches 0. We have 3 minus, when you take the 1 times the 3 plus h, you do get 3 plus h. Be a little careful. You need a set of parentheses around that. Over their common denominator of 3 plus h. And then that's all over. I'll write it as h or h over 1. It doesn't matter. Okay, so we get the limit as h approaches 0. Notice up here we get 3 minus 3, that's 0. So up top we get a negative h over 3 plus h. And now that I've got one fraction, I'm going to go ahead and multiply times the reciprocal of the denominator. So instead of dividing by h over 1, I'm going to multiply times 1 over h. Well, notice that nicely allows me to cancel those h's out. So I'm left with the limit as h approaches 0 of -1 over 3 plus h, which is a rational function. And now notice if I try direct substitution, if I try to plug in 0 directly in for h, what I'm going to get is -1/3. So the slope of the tangent line to the curve y equals 3 over x at the point 3,1 is -1/3, which allows me to find the equation of the tangent line by using the point slope form of the line. So again, that's y minus y sub 1 equals m times x minus x sub 1. So I have y minus the y value, which was 1, equals m, which is -1/3, times x minus the x value, which is 3. So if I clean that up and just solve for y, you get y equals -1/3 x. That's going to be plus 1 plus another 1 for plus 2. So now if you're curious after all that algebra as to whether or not we've got a reasonable answer, let's take a look at the graph of my function and the tangent line that I just found the equation for. So this graph is the graph of 3 over x. Remember, it's very close to the graph of 1 over x. It's a reciprocal graph, except it's been vertically stretched by a factor of 3. And then this is the line y equals -1/3 x plus 2. And if you notice, if we zoom in, it definitely appears as if that line is going to be tangent to this function at the ordered pair 3, 1. So you should be able to verify these visually by graphing both the function and the tangent line and showing that it's tangent at that specific point. So next let's find the slopes of the tangent lines to the function f of x equals the square root of x at 1, 1, 4, 2, and 9, 3. So the good news is with this problem, I don't need the equation of the tangent line. Really all they want are the slopes of the tangent lines. So that makes this just a tiny bit easier than the last example. The bad news is they don't want one slope of a tangent line, they want 3. And I really don't want to do this calculation 3 separate times. That would be way too much work. So what I'm going to do is instead, I'm going to use the h goes to 0 again, but I'm going to go ahead and leave the a generalized. So we're going to look at the limit as h approaches 0 on f of a plus h minus f of a over h. But I'm just going to leave a as a. I'm not going to plug in the different a values. That way I can do this calculation once instead of 3 times. So if we look at that limit, we'll have the limit as h approaches 0. F of a plus h says to take my function f of x, and everywhere I see x, I instead write a plus h. So that's the square root of a plus h. Minus f of a, which says to take my function, and everywhere I see x, I now write a. So that's the square root of a, all over h. So that's setting up my limit. Now I actually need to do the calculation for it. So this goes back to the calculation of limits we've already done. Anytime your limit has a root in it, there's a strong likelihood the technique you're looking for is to multiply by the conjugate. So we're going to multiply numerator and denominator by the square root of a plus h plus a. And this should help us out. Okay. When we do that, in the numerator, we've got a FOIL. So we've got the square root of a plus h times the square root of a plus h. So that's just going to give us a plus h. So we make sure to write our limit in here. We'll have a plus h. Now, you can write these down or not, but notice when you multiply the firsts, that's plus the square root of a times the square root of a plus h. And then this one is minus the square root of a times the square root of a plus h. So those are just going to cancel. That's why you picked the conjugates. They go away. So I'm not going to write them down. And then the lasts, when you multiply them, so you've got a positive and negative, so this becomes a minus. And then the square root of a times the square root of a is a. Notice that numerator cleaned up really nicely. The denominator, not so much, but if you remember, we talked about the fact that you want to leave that h out of it. Technically, it's not mathematically incorrect to go ahead and distribute the h in, but the goal is to cancel it so that we can do direct substitution. So we want to leave it factored out so we can see when we have the ability to go ahead and cancel. So if you notice in your numerator, you've got a minus a, those are going to cancel. So all you're left with is h. Well, that means now I can cancel the h's. In my numerator, I'm just left with 1. And in my denominator, I'm left with the square root of a plus h plus the square root of a. Now that I've canceled the h, now I want to try direct substitution. So if we plug in 0 in place of h, notice that's the cue to get rid of my limit sign because I'm using direct substitution now. What I get is 1 over the square root of a plus the square root of a. Now when you add two square roots together, what you get is 1 over 2 times the square root of a. So what that tells me is that in general, if I want the slope of a tangent line to the curve f of x equals the square root of x, the way I'm going to find that is by taking 1 divided by 2 times the square root of the a value. So notice that means if I want the slope of the tangent line at 1, 1, what does a equal? Well, it's 1. So then your slope at that point will be 1 over 2 times the square root of 1, also known as 1/2. If you do the same thing for 4, 2, what is a in that case? A is 4. A is going to be your x value. So your slope is 1 over 2 times the square root of 4. That's 2. 2 times 4 gets you 4. So that's 1/4. One more to do. For the ordered pair 9, 3, if you want the slope of the tangent line at 9, 3. The slope of that tangent line will be 1 over 2 times the square root of 9, also known as 1/6. So notice when you leave a general, the algebra to simplify your limit is a little bit more complicated than if you had had a numerical value for a. The benefit is that because you've done all the hard work in the algebra by leaving a general, when you want the numerical value of the slope, you just literally have to plug in a number and do a little bit of arithmetic, which is a lot easier than doing this same calculation 3 times over. All right, let's also go back to the velocity problem that we discussed. We talked about the fact that the tangent problem, which is to find the slope of a tangent line to a curve at a specific point, was very closely related to the velocity problem. And the velocity problem was finding the instantaneous velocity of an object at a specified time, at one specific time. We started this off by looking at average velocities. So what we did is we said, okay, we have a function, and instead of being an xy function, the independent variable was time, and the dependent variable was s, it was position. And what we said was if you had a function that was positioned as a function of time, if you're looking for the instantaneous velocity at one specific time, t, so this would be t s of t. So here's a point P, and I'm looking for the instantaneous velocity at that particular point. What you do is you calculate an average velocity. Instead of finding the velocity at a time t, you go beyond that time t by a certain amount, and you find the average velocity between those two times. Well, this is almost exactly the same setup that we have for the tangent problem. Really, the only difference is instead of dealing with x and y, my variables have physical meaning. My independent variable is time, and my dependent variable is a position. So they have physical properties to them. Other than that, it's the same concept. You're looking at average velocity, which is also known as slope of a secant line if you're talking about a graph, in order to estimate instantaneous velocity, also known as slope of the tangent line if you're talking about a graph. So now that we've discussed limits, we can find this instantaneous velocity without having to guess based on the average velocities. The instantaneous velocity is the limit of the average velocities as those time intervals get smaller and smaller and smaller, or as you slide this q closer to this p. This is the example that we completed when we looked at the velocity problem. A stone is dropped from the top of a building 600 meters tall and falls to the earth. Estimate the instantaneous velocity at t equals 5 seconds. Use Galileo's formula that says the distance traveled by the stone after t seconds is given by s of t, there's that position function, equals 4.9 times t squared. So these are the calculations that we did. We said that average velocity was a change in position with respect to a change in time. So we were looking at, these are only averages, so we just needed the changes in the positions divided by the changes in times. So for the time interval from 5 seconds to 6 seconds, here's the 4.9 times t squared minus 4.9 times t squared. There's the difference in the times, etc. These are all the calculations that we did. And what we noticed was that every time we calculated an average velocity, as we made these time intervals smaller and smaller and smaller, so instead of being 1 second long, it's half a second long or 0.1 second long. Look at what happened to our velocities. It went from 53.9 to 51.45, all the way down to 49.049 meters per second. And so we guessed that the instantaneous velocity at 5 seconds was going to be 49 meters per second. So to avoid having to do this with so many numerical calculations, we use the fact that the instantaneous velocity is the limit of the average velocities. So instantaneous velocity at a specific time A is going to be given by the limit of the average velocities. There's s of t minus s of a over t minus a. There's the change in position and change of time. Or if we use the other notation, there's the s of a plus h minus s of a all over h. So this is just the two different notations that we discussed with the tangent problem as well. So let's take a look at an example. This is going to be similar with slightly different numbers. Suppose that a ball is dropped from 450 meters above the ground. What is the velocity of the ball after 5 seconds, given that the distance after t seconds is given by that same formula, s of t equals 4.9 times t squared. So we want the instantaneous velocity of the ball at 5 seconds, but also at 6 seconds and at 7 seconds. Okay, so a couple things to point out first. First of all, this is not always going to be the formula we use for instantaneous velocity. This is only good for an object that is just dropped from a resting position. It is certainly not the case if you were to, for example, launch an object out of a cannon, or even just throwing it off the top of a building would change this function. We're reusing it for ease of calculations. The second thing I want to point out is that we are asking for the instantaneous velocity at 3 different times. Well, if you want to use this formula that we just took a look at, if you want to avoid having to do this calculation 3 different times, we're going to want to leave the time general. So we're going to look at the velocity at a time A. Okay, so we're going to leave that as a general A. And I'm going to use the h goes to 0 one again. So that's going to be the limit as h goes to 0. That's s of a plus h minus s of a all over h. Okay. So when we set up this limit for specific to our problem, we need s of a plus h. That's our function s. Everywhere we see t, we plug in a plus h. So that's going to be 4.9 times a plus h squared minus s of a, which is your function with a plugged in. So that's 4.9 times a squared all over h. So that's the setup. We need to actually do the limit calculation. And again, you can't plug in 0 directly in for h. It's going to give you a 0 in your denominator. So we're going to have to do some manipulation, which in this case is going to involve expansion. If we expand the a plus h squared, we're going to get 4.9 times a squared plus 2ah plus h squared, because remember that's a FOIL, minus 4.9 times a squared all over h. When we distribute the 4.9 in, we get the limit as h approaches 0. We get 4.9 times a squared plus 9.8 ah plus 4.9 h squared minus 4.9 times a squared all over h. So my instantaneous velocity, notice the 4.9 a squareds nicely cancel, and the two terms that are left in my numerator both have an h in common. So we'll have the limit as h approaches 0, h times 9.8 times a plus 4.9 times h all over h. Now that it's factored out, we can cancel it. Notice now that we've canceled the h's, we're now able to plug in. There's our direct substitution. We're able to plug in 0 in place of h, and what we get is 9.8 times a. Well, that's great. That tells me that if I want instantaneous velocity at any time a, all I have to do is take 9.8 times that a. So in other words, if you're looking at a equal to 5, so 5 seconds, if you take 9.8 times 5, you get 49 meters per second. So the instantaneous velocity at 5 seconds is 49 meters per second. If a equals 6, my instantaneous velocity is 9.8 times 6, which is 58.8 meters per second. If I'm looking at a time of 7 seconds, then my velocity at that point will be 9.8 times 7, which is 68.6 meters per second. Make sure you are including labels on these. So that's another example of, by leaving the time general, I did slightly increase my difficulty level as far as the algebra, but when I'm done, the end calculations are very simple arithmetic. So this is by no means the only type of question we can ask you on this. I mean, this is great to be able to find the velocity of an object at any given time. But one of the other things we're going to be interested in is, how fast is this ball traveling when it hits the ground? Okay, and that's another question we're going to be able to answer. Notice the question says, how fast? We are looking for a velocity, specifically an instantaneous velocity. The question we now need to answer is, when does it hit the ground? Because according to the work we just did, we know we can always calculate how fast something is going by taking 9.8 times the number of seconds. So what I really need to know is, when does it hit the ground? After how many seconds? So if I want to know when this hits the ground, think about it. You've taken this object and you've dropped it, and you want to know when it hits the ground. So if I can figure out how far it traveled, I can use the function that says s of t equals 4.9 times t squared. How far did this particular ball travel before it hit the ground? Well, if you look back to the problem, it's dropped from a height of 450 meters. So it's traveled 450 meters when it hits the ground. That's how far it's gone, but this is the function that relates where it is to when it is. So what this tells me is that at 450 meters, it's hitting the ground. That's going to allow me to solve for its time. So if I take 450 and set it equal to 4.9 times t squared, in other words, t squared is approximately, just divide both sides by 4.9, you're going to get 91 point, this is approximate, 83673, etc. This goes on. And then if you take the square root of both sides, you get approximately 9.6 seconds. Okay, so it takes about 9.6 seconds for this ball to hit the ground. So this time should make sense. I mean, we just said, based on the previous example, that at 5 seconds, this was going 49 meters per second. At 6 seconds, it had sped up. At 7 seconds, it had sped up. So it's continuing to move at 5 seconds, at 6 seconds, at 7 seconds. It's going faster and faster. Well, eventually, it's going to hit the ground. So the fact that we got a time of 9.6 seconds makes sense based on the information that we have so far. Now that I know that, if I want to know how fast it's going at that time, what I really want is v of 9.6. In other words, 9.8 times 9.6. So its velocity when it hits the ground is approximately 94.08 meters per second. So now we have examined two different situations where we want to talk about how two things are changing with respect to each other at one specific point or time. I mean, if you're talking about a tangent line, you want to talk about how y is changing with respect to how x is changing. If you're talking about velocity, you want to talk about how position is changing with respect to how time is changing. But you want to do these at one specific point, not over the course of time or not between 2 points. So turns out this is not the only time this is going to happen. This is what we call a rate of change, how one variable changes with respect to another. This concept appears in many applications across numerous disciplines. I mean, you're talking all of the sciences, of course, physics, chemistry, biology, but you're also talking business and manufacturing, you're talking economics. So we're going to examine many of these applications once we're a little bit more comfortable finding rates of change. But turns out, if we're going to use the same concept over and over and over again, we don't want to have to continually say the rate of change of y with respect to x or the rate of change of s with respect to t. We want to be able to shortcut that just a little bit. So we gave it a name. We named it the derivative. So when we talk about a derivative, what we mean is that the derivative of a function f at a number a, which we denote by f with this little tick mark up here of a. Okay, so this is the derivative of f at a. You'll hear people refer to this as f prime at a. The derivative is that limit definition that we just talked about. This is the limit definition of a derivative. The derivative of f at a is the limit as h approaches 0 of f of a plus h minus f of a all over h, if that limit exists. It's also the x goes to a limit. So these are both considered the derivative of a function f at a number a. When you're asked to find the derivative of a function, you can use either one of these limit definitions. Now, for the most part, when we're doing these algebraically, we're going to use the h goes to 0. And I'll actually show you why in the next example. I'm going to do the next example using both. I'll first do it with h goes to 0, and then I'll do it with the limit as x goes to a, just so you can see it's the same thing. You should get the same answer. But usually the h goes to 0 is going to be simpler to manipulate algebraically. That doesn't mean we use it exclusively. The limit as x goes to a has a tendency to be much easier to use if you're talking about a real-world application. So we'll use them both, but for now we're going to concentrate a little bit more on the h goes to 0 limit. But let's start with this. Find the derivative of f at a for f of x equals x cubed minus x. We're going to use h goes to 0, and then I'll do it again for x goes to a. Okay, so the derivative of f at a. So we're going to use the limit as h goes to 0 of f of a plus h minus f of a all over h. So we have the limit as h approaches 0. So here's my function. F of a plus h says to take my function, and everywhere I see x, I write in a plus h. So that is going to be a plus h cubed minus a plus h. Be careful, you do need the parentheses around there. Minus f of a. So minus, that's our function with a plugged in instead of x, a cubed minus a. So again, you do need that set of parentheses. Watch those negatives. All over h. So once we have that set up, we just need to do a lot of algebraic manipulation for this one. So if you want to do a plus h cubed, please make sure you know that is not a cubed plus h cubed. That is a plus h times a plus h times a plus h. So one option would be to do all the distribution that this requires, to take a times a times h times a, h times h, and multiply these first two together, get the result, and then multiply that result and distribute that to a plus h as well. It'll work, it's just a little long. If you remember your binomial theorem from pre-calculus, this gets a little bit easier. This will be, you'll have an a cubed. Your next term will have an a squared and an h. Your next term will have an a and an h squared. And then your last term will have an h cubed. All you then have to remember are the coefficients from Pascal's triangle. And for the n equal to 3, for the power of 3, your coefficients are 1, 3, 3, 1. If you don't remember that from binomial theorem, just do the distribution and you'll get the same thing. So then we do minus a minus h minus a cubed and plus h all over h. So algebraically this is getting a little bit long, but we're getting there. So we want to start canceling out what we can. So I see an a cubed minus an a cubed, minus a and a positive a. Notice I have 4 terms left. I have 3a squared h, 3ah squared, h cubed, and h. Notice they all have an h in common. So we factor out the h, and we get 3a squared plus 3ah plus h squared minus 1 all over h. And those h's nicely go away. So I'm left with the limit as h approaches 0 on 3a squared plus 3ah plus h squared minus 1. Now that I have no denominator, this is now eligible for direct substitution. Everywhere I see h, I can now plug in 0. So my first term has no h, it stays the same. So we get 3a squared. This term has a 0, so that whole term becomes 0. This will be 0 squared, that becomes 0, and then minus 1. So the derivative of the function x cubed minus x at the number a will be 3a squared minus 1. That's the derivative. Now I'm going to redo the same problem using the x goes to a limit, just for the sake of showing you that you will in fact get the same answer, but I think this will also help illustrate why we tend to use the h goes to 0 limit instead. So this is the limit as x approaches a, f of x minus f of a over x minus a. This is the other limit definition of a derivative. When we do it this way, when we set it up, we're going to get the limit as x approaches a. We need f of x, which is your function as written. So that's x cubed minus x minus f of a, which is your function. Only everywhere you see x, you plug in a. So minus a cubed minus a, watch those parentheses, all over x minus a. Now, you may be saying, but that's a lot easier to set up, and I won't argue. That is easier to set up. It's the algebra that comes next that becomes much more problematic. Remember, the end goal is direct substitution. I want to be able to plug in a everywhere I see x. And of course, because of that denominator, that's not possible. If you plug a in place of x, you're going to get a 0 in your denominator. So just like we had to cancel the h in the previous limit definition, we're going to need to cancel the x minus a, which means we need to factor an x minus a out of that numerator somehow. Okay, well, it's got 4 terms. We're looking at the limit as x approaches a. If I distribute that negative, I've got an x cubed, an x, minus a cubed, and plus a, all over x minus a. If you remember the factoring technique for anything that contains 4 terms, if they don't all 4 have something in common, you want to try factoring by grouping. That involves factoring out what's common to the first 2. So that's x. That'll leave you with an x squared minus 1. And then factoring out what's common to the second 2, which in this case would be a minus a. And that's going to leave you with an a squared minus 1. The problem is that to continue on with the factoring by grouping, I need these 2 factors to be the same, and they are not, which means this didn't work. So do you remember what the next step is if that method of factoring by grouping didn't work? The next step is to rearrange those terms and see if that works. So instead of x cubed minus x, you write x cubed minus a cubed. Move this one. And then minus x plus a. It's just a rearranging of those terms. And then you try to factor by grouping all over again. You try to factor the first 2. Well, if you look at x cubed minus a cubed and you want to factor that, that's the difference of 2 cubes. It does in fact factor. If you remember the difference of 2 cubes, that will factor 2x minus a times x squared plus ax plus a squared. That's how you factor x cubed minus a cubed. Minus, when you take the negative out of the x, you get x, and when you take the negative out of the a, it becomes minus a. Now, to recap, these 2 together are x cubed minus a cubed. And then I took a negative out of the minus x plus a. Believe it or not, that's a good thing. Because now what I'm seeing is that if you consider these to be 2 separate terms, each term has an x minus a in common. So you factor that out, x minus a. What you're left with in the first term is the x squared plus ax plus a squared. And in the second term, what you're left with is minus 1. All over x minus a. So I factored the binomial out of each one of those terms. That's what I needed. Now I can start canceling. So now that I've canceled, we're looking for direct substitution. We want to plug in a everywhere we see x. So instead of x squared, we write a squared. When we plug in a for x in the second term, instead of a times x, we get a times a, also known as a squared. There is no x to plug in for here, so it stays a squared. And then we have minus 1. And when you combine those together, you get 3a squared minus 1. Which if you compare that to the previous example, it's the exact same thing we got. So the reason that we use the h goes to 0 limit more often when we're trying to do these algebraically, you need fewer factoring tricks to cancel out an h than you do to cancel out an entire x minus a. So you do get the same answer. They both work, but generally for these, the h goes to 0 is going to be just a little bit easier. So now that we've done that, if we're then asked to find the equation of the tangent line to f of x equals x cubed minus x at the point 2, 6, remember the equation of the tangent line requires 2 things, the point and the slope. We have the point. The point is 2, 6. What we then need is the slope of the tangent line. Well, that's what we just spent the past 2 examples calculating. The slope of the tangent line at a number a is 3a squared minus 1. We just did it twice, so we're really sure. So what is the slope of the tangent line at 2, 6? Well, what is a if we're dealing with the point 2, 6? A is 2. So it's 3 times 2 squared minus 1, also known as 11. So the equation of the tangent line is y minus the y value equals the slope times x minus the x value, which if you then simplify, you'll get 11x. That will be minus 22 and plus 6 for a minus 16. That's the equation of the tangent line. So once you've gone through and found the derivative, you've got the capability of finding the slope of the tangent line at any point.